And so we're going to understand what this is all about. Okay. So, from PChem, you got into p-values when you did an ANOVA table, and we talked about what those mean. And again, there's probably some that didn't quite understand it or didn't quite get it, and are uneasy about that. And so we're going to really solidify your thinking about what a p-value is today. And then we're going to use that thinking, the null hypothesis, in determining the difference between a couple of different analysts. Okay. So we're hiring a newbie at DW Labs. Okay, we have a forensic chemist on staff, and we want to recertify that person on the equipment. And so we go to the vault and pull out a recent seizure that's been analyzed very carefully to be 13.2 plus or minus 0.1% by mass cocaine. So we're going to just use that as our true value, as our accepted standard, and then we're going to have both of these persons to analyze it, okay, and see how they compare to each other. Okay, so we have the trainee and the forensic chemist, and they're going to analyze this sample 10 times each. And so here's the goal of this whole exercise. We want to answer these questions. Are both of them accurate? Are both of them precise? And are they different from each other? So pretty easy to answer the accuracy question. We know the accepted answer, 13.2. Are they off from that? Are they biased? Are they always low, always high, whatever? So that's the accuracy, the percent error. And then also the precision, standard deviation, 95% confidence intervals, those kinds of things. That's easy to do. That's precision. But how do you tell if they're the same? Like, I don't want one analyst to always be biased low and the other one be right on target, because then I got to worry about who gets the samples. And that's the last thing I want, is for my personnel to be attacked on the stand. Like, which one was this, the good technician or the bad technician? You know, that's not a good question to be asked. Okay, and so I want them to be completely interchangeable. I want them to sign the form so I know who did it, but I don't want there to be any question about who's the good one and who's the bad one. Okay, so are they the same? And how do you measure sameness? Well, do they have the same mean? Right? Are they the same in terms of they give the same answer? Or are they the same in terms of precision? Is one really solid and got good precision and the other one not so good? So the test of equal means is the t-test, and the test of equal precision or variance is the f-test. So we're going to learn about those two things today too. So in a perfect world, there'd be no statistically significant difference between the accuracy, which we measure with the means, or the precision, which we measure with the variances, between the lab personnel. So that would be ideal. And of course, we can get close to that. We'll never have a perfectly ideal world, but we can get close to that. And that's why we do trainings and certifications and all of that. We want everybody to be competent and reliable. So here's the results. So it's always good to just look at the results before you start putting things in and calculating math on everything. So you just analyze to see if the results are good. Okay. So everybody, all of these samples were 13.2% by mass cocaine. And so you just look at the data. Is it close to 13.2? I would say yes, right? It's not 100 something. It's not 0.01. Okay. I gave a technician some explosive samples and they went and ran FTIR on them. I had 8 tablets. They ran them all. They didn't run them 3 times. They just ran them one a piece, sent me back the data on a floppy disk. That tells you how long ago it was. And I put the disk in my computer, pulled up the spectra, and they were just flat with some noise. There were no peaks at all. There was some noise in the water region and some noise in the CO2 region. So these are supposed to be FTIR spectra of these explosive samples. And so they sent me the data from the lab, and it was completely useless. And so I went to see how they took the data. I said, show me what you did to analyze these samples, because I wanted to sort of reteach them. So they put the tablet on there. They pressed it down on the top with the ATR. So you guys know how to use an ATR. You push the little post down, push it onto the crystal, and they ran, okay, background. And they ran a background. And then they ran the sample. And then they put the next tablet on, background, sample. So what were they doing? background was the same as the sample. So all the peaks got subtracted out because they were doing the sample versus the background, but it was exactly the same thing. You're supposed to do the background before you put the sample on, and then you put the sample on and hit sample. So I got, baseline to spectra with no peaks. So seemingly insignificant step, right? Whether you put the sample on before or after you do the background, but it makes all the difference in the world. Now, the reason I tell that story is because they never looked at the data. If they'd looked at the data, they would have said, where are my peaks? Right? We didn't need statistical analysis to know something was wrong. So if you look at the data first, just look at it and see, I put in 13.2% and I got 0.011. And in fact, all of them are 0.011. Like my spectra. There were no peaks. It was all zero. Okay, so we look at this and we say, yeah, the trainees here, the forensic chemists here, they're all around, 13 plus or minus some. Can you tell a difference between the two columns? What do you see? Yeah, it seems tighter, doesn't it? So immediately you can see that there's a difference in precision. So there's more scatter in this column. You got some 12s, you got a 15. That's crazy compared to the others. Yeah. And then here you got all these 13s. You got a 13.7, that's the high one. And then 13.1 is a whole bunch of those. So just visually look at the data. Always do that because you'll avoid wasting time. If we looked at this data and it was all, you know, zero point 0.1 or something like that, we would say, Well, first of all, if it was all 0.13, 0.15, point something, you might look and say, well, they may have just forgotten to multiply by 100%. You know what I'm saying? Like that 0.132 is 13.2%. So you may also catch a mistake there too. Okay. And so here's a graphical method of looking at the data. So here's the forensic chemist. Look how tight their data is, what you observed in the numbers. And here's the trainee. Okay, kind of all over the place. And then there's one data point way up there. That's that 15. And then I went ahead and put the green bar is the accepted value plus or minus 0.1. That's the standard deviation and the accepted value. And you can see that they're pretty close. Now this is a graphical result from Minitab. And Minitab uses this little symbol, this little blue mark, to get the mean. So this is the mean for the trainee, and that little blue dot over here is the mean for the forensic chemist. So the forensic chemist, we can see from this graphical method that the mean, the average value is right there within the limits of our accepted value. The trainee's coming in low in almost every case. The only reason it's this average is as high as it is because of this value right here. So I guess the question is, are they accurate? Well, I think that the forensic chemist is pretty accurate because the mean is within the limits. I would say yes for this guy, no for the other one, not so much. Okay, what about precision? Well, precision is the cluster of the data, right? And this precision is way out here. Okay. So what are the benefits of the graphical method of looking at the data? So you put the data, like in this case, this is called an individual value plot. This is your own experience. Like, I'm wanting your words. Like, what do you think this does for you? We looked at the numbers and then we looked at the graphical value. So what benefits does the graphical value give you? Yes. Okay. Okay. The cluster, yeah, well, you can tell just with your eye that the imprecise one is really spread out. Immediately you recognize a precision problem. Yeah, it's so instantaneous, isn't it? So you see a graphical presentation of the data, it's instantly understandable. So if you're ever, called to speak in terms of give testimony and so on, graphical methods are great. okay, to convey a lot of information in a short, digestible piece of information. So now what's the downside of graphical methods? We see the little blue dot for the mean, but we don't have the numerical value. So we don't see the numbers here. We just see the graphical, representation of the numbers. And so the benefits are that it's instantaneous, but it doesn't give us a number for the precision. Like I can't look at this graph and tell me what the standard deviation is here. I know it's big, but I don't have a number, right? So you need both. You need graphical values to convey the information, but you also, for specifics, you need to go back to the spreadsheet and actually calculate the specifics, like the range and the standard deviation and the averages and so on. So here's another type of graphical display of the same data, but this is taken those data points and computed the average and computed the standard deviation, and then created what's called quartiles. So notice the individual data points are not on here. They put these boxes on here. It's called a box and whiskers plot. So this is sometimes just a box plot, but these little things right here are called whiskers. Kind of like a cat, right? A cat has whiskers. And so they go out to the minimum value and to the maximum value. And then it automatically does, in most cases, an outlier test. So in this case, it's determined that this is an outlier. So it'll do a whisker. It won't do a whisker all the way to that maximum data point because it determined that it's an outlier. So it'll stop the whisker at the second highest data point, and it'll put an asterisk there for the outlier. Okay, and that's pretty helpful. And now let's talk about the quartiles. If we were to take the normal distribution, the mean is right at the 50-50 mark. So we have 50% of the data below the mean and 50% of the data above the mean. There's no problem with that, right? Okay, then it also draws two more lines. And so this would be 25%. This is 25%. 25% and 25%. So if we're integrating this all the way up, like we start out at 0%, then we get to 25, then this is 50, this is 75, and then way up here is 100. So you see how it's divided into quartiles, 4 equal groups in terms of probability. And so this is what we mean by the 25th percentile. 25% of the data is below that. And then the median or mean, we'll talk about the difference of those in a second, but the median is right there at the 50th percentile, and then the upper part of the box is the 75th percentile. So the box is this right here. This is the box. It's that range. The median is the middle data point. It's not the mean. The mean can be shifted by outliers, and you see that this mean is a little bit higher than the median because of that outlier. It's shifted up a little bit. Okay, so that's a box and whiskers plot. Now, notice how the box is smaller for the forensic chemist than it is for the trainee, and that's because the standard deviation is smaller. So you can see the size of the boxes and you can get an idea of precision. Or if you're analyzing different samples, the size of the box would be the homogeneity. If the sample is really homogeneous and there's no difference in all the different samples, it'll have a really small box. All the samples are the same. If you got a heterogeneous sample and sample A and B and C, they're all very different, then you'll have a big box. You'll have a lot of variability in the samples. And so you'll be able to look at that very quickly with the box and whiskers plot. Are there any questions on how to read one of these? There are some add-ons, I think, or I think Excel has added the box and whiskers plot as an option, but it's not your standard in your standard insert chart selections. You have to look at other types of charts. Yes. It's so small. It's like right at the edge of the 25th percentile. So you just can't see it. Yeah. If we go back to the individuals, you'll see why. Right here, the individuals. So the bottom three data points all had the same value to one decimal place. And so the whisker doesn't stick out the bottom of the box. Yeah. Okay, so now let's go back to Excel and actually calculate these values. Let's not use the graphical method. Let's actually get in and calculate them. So the very first thing you can do is you can just do the average of each. And so we can look at the average for the trainee and the average for the forensic chemist, and you see they're pretty close, but the trainee is definitely low, 12.9 versus 13.3 for the forensic chemist. Another one is the range. So I've put these formulas in here now. I've done them, C3 and C12 and so on using the forensic chemist column. But if you wanted to calculate it for the trainee, then it would be column B, right? That makes sense. Notice this range is easily calculated. I don't have to sort the data high to low to find out what the high data point is. I can use the Excel formula max. So I can take the maximum in that group of data and subtract the minimum in that group of data. And so there's an Excel exercise. Basically, I want you to go through this lecture and I want you to take the data that's in that Excel sheet and you do all of these formulas yourself. So essentially you'll copy everything I've done today with all of these t-tests and f-tests and range and all the different calculations, just so that you've done it yourself in Excel. Then save that spreadsheet, because in all future data analysis, you will have all of the formulas that you need to calculate the standard deviation, the pooled standard deviation, the F value, the T value, and all of that. So it's just going to force you to go through this lecture with a fine-tooth comb and build that spreadsheet yourself. Now in Excel, they have the the sample and the population standard deviations. And so in this case, we only have 10 data points. And so we're going to use this .s version. So STDEV.P is for the population version. So we're using the divide by n-1 version of the standard deviation. And Excel has that formula built in. So you don't have to take the differences and square them and add them together and divide by n-1, take the square root, and then you've got the standard deviation. Excel has that for you. But you got to pay attention doing the .s or the .p. So if you have more than 14 samples, then you would use the .p. Okay. So the question is, are they accurate? Well, does the average plus or minus the standard deviation contain the true value for the trainee? So here we have our standard deviation of 0.93. So 12.9 plus or minus 0.9 goes from 12 to 13.8%. And yes, this range contains 13.2. So yay. All right, we got the true value within our error bars. And then what about the forensic chemist? Well, 13.3 plus or minus 0.2, look how small their standard deviation is. Goes from 13.1 up to 13.5, so yay, this one also contains 13.2. So they're both, we would consider accurate, although I have a problem with this number right here. And I'm curious about that one, that 15. Like they may have gotten lucky. All their data was low and they had one outlier, and that stretched out their error bars so that they captured the true value. Okay, so there's more to look at in this data exercise. All right, so they seem to be accurate because their means and standard deviations contain that accepted value. So let's talk about the hypothesis testing before we get into testing that outlier. So here's our options. We can't really determine the truth. We have to use our instruments or the data to determine the truth and to sort of give us insight into that. But we can't really know if that's an outlier or not. If we don't have any record or any observation that that sample was spilled or tainted or changed in any way, then we have no way to know if it's truly an outlier. We have to use a statistical test. And whenever we're using statistical testing, we have the null hypothesis, sort of the baseline assumption, and then we do a test to see if it's probably true. So we're looking at probabilities. So these are our only options. We can reject that baseline assumption, or we can fail to reject it. So we're trying to reject it, okay? And we either are allowed to reject it or we fail to reject it. And so in this case, for our outlier test, this is the null hypothesis. Okay. That the data point is not an outlier. And so then we will do a test to see what's the probability that it's not an outlier. Okay. Then we're going to have some other null hypotheses. So the trainee and forensic data sets are from the same population. Okay. Meaning there's no distinguishable difference between their means. They have the same means. And we would use the t-test for that. And then the trainee and forensic chemist data sets have the same variance. So that's their standard deviation squared. So if they have the same precision, they'll have the same variance. We'll use the f-test for that. So these three things are the three null hypotheses that we're going to use in our testing this morning. So let's look at this. Once we have that null hypothesis, we do a statistical test. And if the probability that the null hypothesis is true is less than 0.05, in other words, 5% chance, then we reject that null hypothesis. So it's a pretty stringent test. If it's 5% possible that the data point's not an outlier, we're going to keep it. So there needs to be less than 5% chance it's an outlier. Less than a 5% chance that it's not an outlier. Okay, so if the probability is less than 5% that the null hypothesis is true, then we reject it. Okay, this 0.05 is called alpha. So you'll see a lot of times when you're looking at statistical tests, they'll say alpha of 0.05. That's that criterion. Sometimes they'll say an alpha of 0.025. So that's like a 2.5% chance. And our two-tailed test will have that one. Sometimes they'll have an alpha of 0.01, which will be 99% confidence. So 1 minus alpha is your confidence. So in this case, 1 minus 0.05 is 0.95. That's our 95% confidence. Okay. If it's greater than or equal to 0.05, we fail to reject the null hypothesis. So you have to know what the null hypothesis is to use p-values, and you don't have any business doing statistics if you can't explain, like very concisely, what's your baseline assumption? What's your null hypothesis for this test? If I'm ever in one of your talks, I'm going to ask you that. If you show a p-value, I'm going to say, okay, you've shown a p-value. P stands for probability. It's a probability of what? What are you testing with that probability? And you need to be ready to go. Okay. If you stumble on that, then no one's going to believe your results because they don't believe that you know what you're doing. So you really have to be able to quickly and concisely state what your null hypothesis is. So let's look at this. So this is, we're going to do two different types of outlier tests. And again, if you know you spilled your sample or whatever, you could throw that out. It's a bad sample. But this is for those cases where you have no idea, there's no known reasons for that data point being at 15 when all the others were below 13. So here's what we do. We calculate this Q experimental, and this is the gap over the range. And so it's the questioned data point. So this is the one that's 15. And then we go back to the data and we find the nearest one. And then we divide by the range. And that's our Q experimental value. And we compare it to the critical value. If Q experimental is greater than Q critical, then we reject the null hypothesis. And now you got to pick a particular row in this Q criticals for the number of values, And so we have 10 data points right here, and we want to operate with an alpha of 0.05. And so we find in the table that intersection of 10 data points and 0.05. So 0.466 is our critical Q value. And so then we calculate that. So let's go. I'm going to jump ahead to here. We've got the maximum value here. That's the 15. And the nearest one, we can look at all the other data points. We got 11.5, 13.2, 12.6, 12.9. Here's a 13.3. So that's the nearest neighbor. So that's this one right here. So we take that gap, 15 minus 13.3, and then we divide it by the range. And so then we calculated that Dixon's Q, and it's this one right here. We calculate that value, and it's 0.486. And our critical Q value was 0.466. So 0.486 is larger. And so it is the null hypothesis that it's not an outlier is rejected. So it is an outlier. That's the thing that makes this very confusing, is because you have all these double negatives, right? It's not an outlier. Okay, so it is an outlier. Okay, so let's go back up here and do the Grubbs test. So the Grubbs test is recommended by the ISO and also the ASTM. It's based on the Gaussian normal distribution. And so we have we take that question data point. So in this case it would be 15, and you subtract the mean and divide by the standard deviation. And then here our critical value is just those sort of multipliers of the standard deviation. And so our 1.96, that's another nice thing about this test is we've remembered or memorized this Z value for our confidence intervals is 1.96. And I told you a couple of lectures ago that that number is used so much for 95% confidence, you should just memorize that one. So instead of plus or minus 1 standard deviation, plus or minus 1.96 standard deviations captures 95% of the data. And so what this is saying is if that data point is outside that 1.96 times sigma, then it's likely an outlier. And so we can compare that. Again, our null hypothesis is that it is not an outlier. If your Z questioned is greater than Z critical, then reject the null hypothesis. So let's look at our data points. Here we take the 15 and we subtract the mean, 12.9, and then we divide by the standard deviation, and we end up with 2.30. So our data point, 15, is 2.3 standard deviations away from the mean. And the upper limit for 95% confidence is only 1.96. So it's beyond 1.96. It's at 2.3. So it's likely an outlier, right? You've got this Gaussian curve, and 95% of our data points would fall within that Gaussian curve. And here we have one that's way outside those limits. So we would say, yeah, that 15 is outside the 95% limits. So it's an outlier. So this is our conclusions, that the Grubbs test would call it an outlier, and so would the Dixon's Q test. Now, y'all may not have noticed, but in the Forensic Chemist, we had a 13.7, and it has a nearest neighbor of 13.5, and all the others are 13.4, 2s, and 1s, okay? So let's test those. Well, the Grubbs test says that 13.7 is 2.15 standard deviations away from the mean. So it's an outlier according to the Grubbs test, but according to the Dixon's Q test, it's not. Okay, so here we have opposing opinions, Grubbs versus Dixon on that data point, and so we would probably keep it. It may be at 95% confidence an outlier, but probably not at 99% confidence. That's just the next highest data point. Yeah, so if you looked at all the data points, the 15's up here, what's the nearest neighbor? So the very next one is the 13.3. Yeah, and the same for the forensic chemist. I just did this sort of to make it easier to display. It happens that the nearest neighbors are on the same row and the maximum's on the same row. But I did that just on purpose so it'd make it easier for me to show. But somewhere in there would be the next nearest neighbor, and you would pick that one. Yeah. Good question. Yeah. So here we're sort of being conservative here for the forensic chemist because, again, for the Grubbs test it says it's an outlier. The Dixon's Q test says it's not. And so we're going to keep it. We're going to fail to reject that null hypothesis that it's not an outlier. So we'll fail to reject that. But on the 15 data point, that's clearly an outlier with both tests. So we'll throw it out. So now we're going to have 3 columns. We're going to have the original column, and then we're going to have that. If we get rid of that outlier, we'll have a different number of data points, a different standard deviation, a different mean, and all of those things. Okay, so let's look now at the precision and accuracy changes without the outlier. So here we have this, we have the absolute error. So we're 0.33 low. And notice that the error is the mean value from our experiment minus the true value. It's important to get that order correct. Okay, so it's the mean from our data points, and we subtract the literature value or the true value, because if the literature value is higher, that's going to be a negative number, meaning that negative sign shows that we're low. And so if we were a higher, then that would be a positive result, and the positive sign would mean that we're high, we're above literature. We don't want to get that order backwards because then the plus and minus signs will be reversed. Okay, so let's say we were below literature and literature was being subtracting our mean, then we'd have a positive result, but we're actually low. And that doesn't feel right. You know, if we're low, we need to see a negative error, and if we're high, we need to see a positive error. So keep that in mind. A lot of people mess that up. And then if we want to do the percent error, we take that difference and we divide by the true value. So it's always the more certain value is in the denominator. So if literature value or true value is the certain value, we take the difference and divide by the literature value or the true value. That's the thing that we want to know. What percent of the true value are we off? Okay. And so this says we're low by 2.5%. 2.5% low. Now, some people don't like to deal in numbers. They like words, okay? Juries like words, okay? So, but you need to have a key, right? And so this is my key. It seems, I guess, this is how I've heard people talk about these numbers, okay? I'm putting it down for you now, that if you're off by 5%, that's pretty poor, okay? If you're between 2 and 5% or 2 and 4.9, I would call that fair. And so here the trainee is low by 2.5%. And so I would say that's fairly accurate. It's not poor accuracy. Greater than 5% off would be poor accuracy. So it's fair, okay? If you're within 2%, that's good. And if you're within 1%, that's excellent. So excellent accuracy would be within 1% of the true value. So this is just, again, this is my distillation of what those words would mean. It's not in a standard anywhere. I'm sure there are standards that would tell you how to converse about that, but this would be my recommendation. Okay, so let's look at this. Are they precise? So the standard deviation is 0.88. The RSD is 0.072. I got that by dividing the standard deviation by the mean. And so our CV, our coefficient of variation, is 7.2%. Our confidence interval, plus or minus 1.96 of that value, is 0.166. So there's our confidence interval range. And so going off of this 7.2%, I would say that the poor trainee has poor precision, using my little table up there. Okay, so the precision needs to be improved for my trainee. Let's get rid of that outlier and see what changes. Okay, so we get rid of that number 15. and redo the mean, redo the standard deviation, and all of that. Now that would be really tedious if you're using a calculator, but in Excel, you copy all those columns over with their formulas and delete the 15, and now everything's redone. Okay. So now our percent error, because that point was pulling our mean up, we get rid of the 15, and everything drops, and our percent error dropped to 4.3% low now, which is still within 5, so I would say it's fair accuracy. The standard deviation improved because we got rid of that outlier, and so now we're up to fair precision, 4.6%. Let's look at the forensic chemist now. We're going to keep that data point, that 13.7, because of the 2 conflicting tests, and now our percent error is 0.5%, so that's excellent according to my little table up there. And then our coefficient of variation is 1.5%, and so that's very good. So there's definitely a difference between our precision. We have good precision here and fair precision on our trainee. Plus we had an outlier on the trainee. We have fair accuracy and excellent accuracy. So we would say there's a difference in accuracy too. So what about pooled standard deviation? Well, we have two analysts. One did 9 samples if we throw out the outlier. The other did 10. And so let's pool them together and get a standard deviation for the lab itself. Okay, so this is the pooled standard deviation equation. And so remember, for one of the analysts would be, this would be 9 minus 1, and this would be 10 minus 1, because we dropped out that outlier. Okay. And we need to use that pooled standard deviation to do the statistical t-test to determine if their means are the same. Okay. So we have to do this. So let's go ahead and look at the numbers on this one. So for the t-test for equal means, the null hypothesis is the trainee and the forensic chemist data sets are from the same population. So what that's the statistical language, but what it means is you have this overall Gaussian curve, that's the population, and you have the trainee and the forensic chemist, and they're close enough that they would fit under that big curve. Does that make sense? If they're not close enough, like this, our big curve would look like this. It would have a bump here and a bump here, and that would be called bimodal data. There's 2 maxima, and this is what it's testing for. It's like we got these 2 data sets. Are they far enough apart that we have bimodal data? Or are they close enough that we just have a single maximum, a single population? So that's the question. I mean, we know that they got their samples from the same packet, right? So that's not what we're asking. We're asking, is there something in their data that's biasing things? Maybe the trainee has a funky pipette technique or something, and it's shifting the population of their samples so that it appears to be from a completely different packet. It's from the same packet, we know that, but it's their technique that may be shifting things. So we calculate T experimental, which is the difference in the means divided by the pooled standard deviation times this sort of looks like a reduced mass almost with their data points. Okay, since our trainee could be high or low, we have a 2-tailed test. So this makes our alpha 0.025, half of 0.05. And so this is the equation that we use in Excel to get that. So our trainee had 9 data points. That was 10 minus the outlier. And so then 9 minus 1 is 8. So we put the degrees of freedom in this equation and the 0.025. So we have 0.025 on either side of that Gaussian distribution. So that's how we get T critical. Okay, and if our T experimental, which is calculated up here, is greater than T critical, then we reject the null hypothesis. You could also find T tables. You can find the critical T values here. This is the 0.975. So that's 1 minus 0.025. And we have 9 data points. And so here's our critical T value right there. So we can use that T inverse equation. Now I have this one here at 9 because it's doing it for the trainee with the outlier, but it would be 8 if you're doing it without the outlier. And so here we have our pooled standard deviations. So we had this for the trainee. We had this for the trainee without the outlier. We have the t-test, which is that absolute value of the difference in means, and then all those data points and so on, divided by the pooled standard deviation, and we get these t-test or t-experimental values. So these are the t-exps. And then here's our t-table values, our t-criticals are right here. And you see in both cases our t-experimentals are larger than the t-criticals. And so our conclusion is the means are not the same. Even when we got rid of the outlier, it made the means worse actually. So we already knew this by looking at the percent errors. Okay, one was fair, the other was good. Okay, but this is a numerical value that's unquestionable. Like we actually have, it's not DW's gauge of how good something is, right? It's a t-value, and it's gonna be a critical test that tells you yes or no, are they the same? So our question 3, are they the same? They're not the same in terms of their averages. Now let's do the F test for equal variances. So this is the null hypothesis that they have the same variance, which means they have the same precision. We know this isn't going to work out, right? Because even from the very beginning, when we looked at the data, the trainee had data points all over the place, 12s and 15 and 13s and so on. But this is a numerical test of that. So this one, it's very easy to do. We calculate this F experimental by just looking at the variances. So it doesn't matter which one's on top. So you take the variance for one and divide it by the variance of the other. Okay. Since our trainee could be high or low, depending upon which one you put on top, we have a two-tailed F test. So we have two alphas. We have 0.025 and 0.975. Think about that. If you've got your Gaussian curve, and this is 100%, right? So we've got 2.5% here and 97.5% here. And then the middle part is 95% in this area. So that's what the 0.025 is and the 0.975 is. It's those two limits. And so here's the upper critical value. Notice what you have in here. You have your alpha. You have the trainee without the outlier. So that's 9 data points minus 1. And then this is the forensic chemist, 10 data points minus 1. And so we get this value for the upper critical value, 4.1. And then it's the same equation, 8 and 9, but it has a different alpha for the lower critical value, and it's 0.23. And so this is our test. If our F experimental is between those two limits, then we do not reject. So we have the lower is 0.23 and the upper is 4.1. And we do this ratio here, and we compare it to those limits. If it's inside those limits, we don't reject it. Okay. So let's go calculate it. Here's our variances. And then with the outlier, that ratio is 21, way higher than 4.1. Okay, if we throw the outlier out, it gets way better, but still, it's 8.35, and it's still much greater than 4.1. So in those cases, that the F is greater than the upper F critical value, and so the variances are not the same. So now we have a statistical conclusion, one we can stand on in the court of law and say, yeah, these two personnel have vastly different precisions and statistically different means, and so they need to be retrained until they come into line with each other so that they have statistically similar means and statistically similar variances. So we need to do what they call walk the line. So we have this experiment go again. Let's do maybe 5 more data points, or maybe do 10 again, who knows. But as a manager, I would go and I would watch the forensic chemist first, and I would have the trainee with me and see how they do all of the procedures, because there's something happening between the sample, which came out of the same safe package, and the results. And then I would watch the trainee and see if they were doing things in a distinguishable way that's different or the same as the forensic chemist. Okay. So these are the null hypotheses that we used so far. The trainee and forensic chemist data sets are from the same population. We rejected that because they were with the t-test. And they had the same variance. We rejected that with the f-test. You can do this in Minitab. So we did it all in Excel. That's fine. Save that spreadsheet and you have it in the future. In Minitab, you can go in, you have your data in these columns, and you can do a 2-sample t-test, and you just select the columns that the data's in, give individual plots and box plots of the data, and it'll tell you the f-test. So this is the probability that they're the same. Okay, it's 0 probability that they're the same. Okay, and so the trainee is significantly different. Yeah. Okay, now let's talk about the sampling plan. So if we were to, let's say we get these two personnel to be indistinguishable from each other. Oh, can I get you to close it? And so then we have a large collection of samples that comes into the lab. How would you sample those things? Well, there's this guide for uncertainty management that's accepted in the forensic science community, and there's also ASTM for guidance. And so what they have in those is you would inspect and sort the incoming evidence, and then you would decide on the number of analyses you need to do. Okay, and so this is our expected uncertainty and the acceptable error. And so this is kind of tricky, because how do we know what the expected uncertainty is in a bunch of seized samples? I don't know how good this drug dealer is in making up his little packets, right? So what is the expected uncertainty packet to packet? Who the heck knows? So even though these are very scientifically produced, it's very difficult to use them because you've got unanswerable questions. And so the bottom line is this. You might say, well, let's just be conservative, and if we have 100 samples, let's just test 10% of them. Time is money, and so is instrumentation and solvents and all of that. So it doesn't make sense to sample 100%. So if you look at 100 packets and you see that they're all indistinguishable, and that's the key, you look at them and you say, all right, 100 packets, they're all clear, all white powders. You look at the powders, make sure that one's not clumpy and gravelly and the others are all fine and well ground. That would be a distinguishable difference. And so you sort them into groups of indistinguishable types. And those would be seizure, subcategories. And then you decide how many of those subcategories you're going to sample. So a 10% rule is pretty common, but it's not ideal, and necessarily, let's say you get 10 packets, 10% would just be one packet. That doesn't feel right to have 10 packets and only test one of them. So what do you do in that situation? So this is a good bottom line for a large lab, if up to 20 samples in a lot, so like if we have, say, a whole bunch of samples and we break them into distinguishable lots, then if we have 20 samples or less, we're just going to run all of them. Put them in the auto sampler tray, let it go. So we got all 20 of them analyzed. Okay. And then if there's more than 20, we would test 10% of the remaining. So we're going to test all of them up to 20. But if we have 30, okay, we're going to take those 30 samples and we're going to pick out 20 of them at random. All right. Now there's 10 left. And we're going to sample 10% of what's left, which is 1. So we're going to sample 21 of the 30. That's pretty good. We will know what those 30 packets are. And we will see if there's like 2 groups or if they really are indistinguishable. We analyze the data, we look at it, we're like, yeah, this all looks like it, plot a histogram of it. You say, yeah, it looks like it's all one unit, one population. This is more conservative than the 10% rule of thumb. And so this is our equation. So you see this, we would sample the lab samples we would make up would be 20 lab samples plus 0.1 times anything that's left over above 20. Now let's look at this. I put a new slide in this morning. So as an example, a trunk full of drugs were seized and there were 500 tiny bags of white powder. We're not going to sample all 500 of these packets. That's a lot, okay? 400 bags were clear, so we inspect them all, look at them, and 100 bags were tinted blue. So what's your plan? Yes.
That's the tinted blue bag.
Yeah, and then what? What do you do with the clear ones? Did you say? I didn't hear.
No, I didn't.
Okay. Yeah, so we definitely test the tinted blue ones, but also we got to do something with the clear ones. What else? Who else? Yeah, so so the white powder's in all of them. So the white powder's in all of them, but some of the bags holding the white powder are tinted blue, and other of the bags are, yeah. So it's 500 tiny bags, and 400 of that 500 is in clear plastic, and 100 of that 500 is in tinted blue plastic. Yeah. So break it into 2 groups. Yeah. So we have a group of 100 and a group of 400. Okay. Does that make sense? So now how do we test it? So our plan for in clear is equal to 20 plus 0.1. And so the clear ones are 400, right? So we have 400 minus 20. That's 380. So 380 times 0.1 is 38. So it's 20 plus 38. So that's 58. So we would test 58 packs out of the 400, which is again more than 10%. 10% would be 40 packs, okay? And then for the light blue, again, it's 20 plus 0.1 times 100 minus 20. So that's 80. Times 0.1 is 8. So that'd be 28 packs of the 100 tinted blue packs. So we would test those, make up our samples, put them in the auto tray. We have a calibrated instrument. And so then we put all our samples. Now that's a lot. That's 58 and 28. So total, we got 16. So then that's 66, 86 packs. And so we're not going to run our calibration samples and then have 86 unknowns. We're going to want to put a check sample in there every once in a while. So we might do 20 and then put in unknown concentration to see if our instrument has drifted. And then we'll go along and we'll do 20 more unknowns, and then we'll put a check sample back in of a known concentration. So we're looking at our results, and we see our data points for all of these individual unknowns coming in, and then we have our check sample, and it better give the amount it should, right, to test to see if our instrument has drifted. We might throw a blank in there too to see if we're getting carryover. Maybe some of these concentrations are really high and above our concentration chart, and there's still residue on the instrument, and that would be called carryover. So we put some blanks in there to test for carryover. And so our blanks should be 0, our spike or known samples should be known. A spike is when you add a certain amount to an unknown, and so we should see the appropriate jump in concentration. So now, what about this situation? A large 1 kilogram block of strong smelling goo was seized. How would you sample that? Right? It doesn't have countable pieces. Well, you would consult the scientific working group on drug analysis for guidance in that situation. But in general, you divide it into smaller portions. You look to see how homogeneous or heterogeneous it is. Maybe it's some sort of plant-like matter that's been wrapped up, or some of this tarry heroin extract. And so, again, it's not countable samples. So it provides a kind of a difficult situation. But I would say if you got a big block, cut it into 10 pieces and open them up and take photographs to see, does it have striations? Are there discolorations and so on? Maybe you sample, if it's got some light bands through it, you sample the light bands and make a sample of the light colored stuff, and the dark black stuff, you make separate samples. And so you use your ideas of kind of like we did with the tinted blue packs and the clear packs. We separated those different colors and we analyzed them separately to see what information is there. Now, this is interesting. The guidance that I read, it said, take that, break it into pieces, sample maybe, half a gram from each of those 10 pieces, and make up a single lab sample in a solvent. Maybe you extract it if you've got leaf matter and stuff like that. Don't stick that in your GC. Okay, you want to extract it and filter it. So maybe you want to do a liquid extraction, and we're going to cover that in a future lecture on how to clean up samples. Okay, and then you would analyze it. So, but it's still the same kind of idea. We take this enormous block, which we can't sample the whole thing, break it into parts, observe to see if there are, sections of it that are lighter colored, darker colored, or what have you. Then we can sample those different sections and then keep good notes. Of the lighter colored section, this is the chemical analysis. Of the darker colored section, this is the chemical analysis. And then we can compare that to our experience and our data. Okay. All right. So any further questions? I expanded the results on number 8 for the homework a little bit. So if you did the math right, it should definitely be counted correct this time. Yes. I'll give it. So no note cards in this course because people were cramming all their vocabulary on there and they weren't having to memorize things that they need to memorize. And so that's why we don't have note cards in Forensic Chem. But I'll do you a good deed and I give you a whole page of every equation that's been in the notes. And so if you're familiar with the notes and if you've done the homework, all the tools are there. You just got to know how to use them. And then all of the vocabulary and things like the Fry rule and the Daubert decision and so on, those things you have to have up here with you. Okay. Yes?
Are there anything else multiple choice?
A multiple choice. And there may be, on occasion, a written out problem that I have you do. Yeah. But it'd be like 10% of the tests would just be written. But I like to be able to get your grades back to you quickly. So it's mostly multiple choice. There's like 3 or 4 people that still haven't done their data choices. 85 or so% of you guys have gotten a yes from me, so you can start collecting data. Okay, and I'll put up the control chart page here soon, so that you'll have a tab with your initials on it. You go in there and start building your data on that tab. The reason I do it all in a single spreadsheet because I want you to look at your peers' data. So like poke around on there and see what other people are doing, how they're setting up their tables and so on. And I'll show some examples of some good tables and maybe some examples of some bad tables. Don't be embarrassed. I'm going to say, don't do your data this way. I'm trying to help you out. Okay. And so then, copy the best practices of your peers. That's exactly what you do in a standardized industry. If you've got a lab that is a superstar lab, you're going to want to copy their procedures, copy their practices, their training, because you want to be just like them in terms of your results and your reliability. Okay, so let's start thinking that way now.